What are the best ways to experimentally measure nonlinear damping? Imagine you're trying to understand how a system loses energy when it vibrates, but not in a simple straight line. Instead, the damping force depends on how fast or how much the system moves in a complex way. That's what nonlinear damping is all about. Figuring out how to measure this kind of damping can be tricky, but there are some proven methods that work well. Let's explore the most effective ways to do it. One common approach is to look at free vibration decay. You excite the system, then let it vibrate freely. You record how the displacement or velocity drops over time. By fitting this decay to mathematical models, you can see if the damping depends on velocity raised to a power, like squared or cubed. This method works especially well when you want to detect small nonlinear effects alongside linear damping. It's simple to set up and gives clear results. Another technique involves applying a sinusoidal, or smooth wave, force to the system. When you do this, the response often stays nearly sinusoidal even with nonlinear damping. Using harmonic balance methods, you compare the response at different excitation levels. This helps you estimate an equivalent linear damping value that changes with the amplitude. It's a handy way to get a quick picture of how damping behaves at various vibration intensities. Time frequency analysis is also very useful. It involves advanced signal processing tools like Wavelet transforms or Hilbert transforms. These methods analyze vibration signals in both time and frequency domains, allowing you to see how damping changes during transient vibrations. They are especially good for structures where damping varies over time or with vibration amplitude, like in damage detection or structural health monitoring. Modal analysis is another solid choice. You excite specific vibration modes and measure how quickly they decay. If the decay rate varies with amplitude, it indicates nonlinear damping. By taking measurements at different vibration levels, you can build a detailed picture of the damping function. This method is popular in civil engineering and aerospace applications. You can also measure frequency response functions by applying harmonic forces and recording how the system responds across a range of frequencies. Then, you update a mathematical model to match these responses. This process reveals damping parameters, including nonlinear effects, especially in complex systems. It's a detailed approach that provides a lot of insight into how damping distributes throughout the structure. For systems where data-driven methods are preferred, neural networks or fuzzy wavelet models can learn damping behavior directly from input-output data. These black box models are great when the damping mechanism is complicated or not fully understood. They can adapt to different systems, including dampers with special properties like magnetoreological fluids. In microelectromechanical systems, measuring nonlinear damping involves observing tiny oscillations of microstructures. Techniques include analyzing how the damping ratio varies with velocity and displacement, often by monitoring fluid films or other small-scale effects. These methods can detect very subtle nonlinear damping components. When choosing a method, consider the system's stability, the excitation amplitude, and how complex the damping behavior is. Some techniques requiring more sophisticated equipment or data analysis, but they all help you understand how energy is lost in nonlinear ways. This knowledge improves the design of vibration isolators, rotor systems, aerospace structures, and tiny devices where damping plays a big role in performance.